Hello, my name is Said Tabatabai, and this is my Lab 3 report regarding magnetic fields, and the title of the lab is Magnetic Bar Field. The main purpose of this lab is exploring the correlation between the magnetic field value and the observable distance measured during the experiment. We will be doing this both on and off the axis. In order to do so, we have to further understand the Biot-Savart law, which relates displacement and the magnetic dipole moment. During this experiment, we found out that the magnetic field ratio to distance is 2.45 and the magnetic dipole moment is 1.199 joules per Tesla. The two main concepts that we're going to be using in this lab is first the Biot-Savart law, which we can see the formula for it to the right, and second is going to be the physical model of a magnetic field. The two main variables that we're going to be looking at are mu, which is the magnetic dipole moment, which points from south to north pole, and r, which is the observation vector. We can assume that all terms are constant except r. By doing so, we can assume that the magnitude of the magnetic field of the magnetic bar is equal to k times r to the power of n. Based on the lab procedure, n is expected to be -3. And we will be confirming by this by comparing that value to the experimental value. To simplify our calculations even furthermore, we can turn the above equation into a natural log equation, which is shown at the bottom. For the procedure of this lab, we began by determining the direction of the Earth's magnetic north pole by setting the x component measured by the app on the phone to 0 by changing the direction of the phone. After that, we set up a measuring stick perpendicular to the phone, facing east and west. After that, we located the magnetometer on our phone by minimizing and maximizing the absolute x and y values shown on the phone screen of the net electric field. Then we moved the phone along different distances and in different directions and measured the net magnetic field in the closest distance to the magnet on axis and at a 45-degree angle. Then we imported the data into an Excel sheet and took an average of those magnetic fields. We also found out that when we get closer to the magnet, there's an increase in the magnitude of the magnetic field in the x direction. As you can see on this slide, we use the natural log of the magnetic field in the x direction and a natural log of the distance to determine a slope and a y-intercept for the equation mentioned above. Ln of k was equal to -13.046. By reordering that equation, we can set k equal to e to the power of -13.46, which is mu naught over 4 pi times 2 mu over r cubed, which equals to 2.159 times 10 to the power of -6. From that, we find out that our n value is -2.4458 and the percent error is 18.47%. We also find out that the mu value is 1.199. This is the setup of the off-axis part of the experiment, and we had to correct the y component using the Earth magnetic field, which in this case we had to add it to the already existing magnetic field. The average perpendicular distance was 0.2046 meters, and the average magnetic field was 6.043 to the 10 times 10 to the power of -5. And this is a screenshot of my GlowScript code. On line 34 till 38, we define a function of dipole B, which basically implements the Biot-Savart law into our experiment. I also wrote lines 80 to 98 to draw 4 arrows to represent the magnetic field perpendicular to the axis. As you can see, our measured magnetic field differs significantly from the one that we got from our GlowScript code, which introduces different ways of introducing error into the experiment. And finally, we'll get to the questions and conclusions. What if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Other readings would have been transferred according to the direction of the magnetic north. they would be basically on a on a different axis. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The direction of the magnetic field would be the same, but the magnitude would be approximately double if we assume that the two magnets are completely identical.